Okay, so we're looking at this problem here. It's a cantilever structure, series of loads, and a point moment at the end. And we want to know the shear force and bending moment at point C. So we've talked earlier, if I cut this at C, do I want to work the right-hand side or the left-hand side? The right-hand side is going to be advantageous because I don't have to worry about the reactions. So when I cut the structure, I'm going to work the right-hand side. The other consideration is since I want it at C and there is a load applied at C, and really can't, as we talked earlier, can't really cut it at that point, I'm going to cut it just to the left and then just to the right. So let's start with the just to the left. So when I do that, this is what my free body diagram will look like. So there's the object. And since I'm cutting it just to the left, so small, but I get the 500-pound force at C, and then there's a 500-pound force at D, and then again another one at E, and then we have this moment applied at the end. I'm going to go ahead and turn that into 2,000 pound-feet, so all my units are the same. And then this will have dimensions of 10 feet and 10 feet. Again, that little sliver just to the left is really nothing that we can measure, so it doesn't affect the length. So now on this internal face that I just cut, I'm going to make my assumptions of positive shear force. I like to put a little plus there to remind you that I am assuming the positive direction. I said positive shear force. That's positive axial force. This is positive shear force. And this is positive bending moment. So 3 unknowns, and I can write 3 equations of equilibrium. So now I'm going to write my equations of equilibrium. I'm going to start with, at the cut, I'm going to sum the moments. So this is now an equation of equilibrium, so I can choose whatever sign convention I like. I'm going to use right-hand rule. So now I'm going to sum the moments at the cut and make sure the body's in equilibrium. So with this sign convention, what kind of moment is that? Positive or negative? It's negative. So I'm going to write that as negative M. Does this 500-pound force create moment about the cut? No. What about A and B? No. So I have these 2 500-pound forces. What kind of moment did they create about the cut? Positive or negative? Negative. So I'm going to have negative 500 pounds times a moment arm of 10 feet. Minus 500 pounds again, times a moment arm of 20 feet. And then out here on the end, this applied moment, is it positive or negative? Negative. So I'll have minus 2,000 pound-feet. So solve for M. When I solve for M, I get a negative, is that 17,000 pound-feet? No. Yeah. Is it? 17,000?
Yeah.
That's negative 17. I'll go back to kip feet. So what does that mean? Is it a positive bending moment or a negative bending moment? It is negative. Remember, I assumed positive. I got a negative value, so it's negative bending moment. What's negative bending moment? Is that kind of smiling or frowning? Okay, so let's look at this beam. How is this beam going to deflect? Is it going to go up? No. It's probably going to deflect something like that. And what does that look like? That's a frown. Negative. Yes?
So why did you say the shear force will not create a moment?
Well, the shear force is acting right on this face. So if I sum moments there, it has no dimension.
Oh,
There's no moment arm. That's why you don't sum moments over here, because the shear force would create moment anywhere else but the cut. That's okay. It's a good question. So now I'm going to sum forces in the y direction. Assume up is positive. And what do I have? Well, I have my shear forces up, and I have 1, 2, 3, 500-pound forces, and they are acting down. So I'll call those negative. And then what else? That's it. This moment's not a force. So when I solve for that, it looks like it says the shear is equal to 1.5 kips. Right? So the shear force is positive. Positive shear force.
How would you use the moment negative in the calculation? Why is it negative and not just n?
Say that again, Mr. Preston.
Where you have negative n minus 500 pounds times 10t.
Right. Well, remember, now I'm writing an equation of equilibrium, right? And I assume that anything rotating counterclockwise is positive, and that moment is not rotating counterclockwise. So it has to be a negative moment.
You can make a different assumption for your calculations.
Yeah, you could assume that clockwise is positive. This would be positive, and all these would be positive, and you'd still get a negative value for your answer.
Okay.
All the signs would change, right? This would be positive, 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 positive. You'd still get this result. So it's really not important what sign convention you choose for your statics. What is critical is that you choose the right sign convention for your initial unknowns. You don't get any choice there. When you communicate to another engineer and you want to tell them whether this is a positive or negative bending moment, underline bending, bold bending, italics bending, not moment, bending moment, you get a sign convention. Now when I'm over here just summing moments, I can do whatever I want. And I choose right-hand rule. But it wouldn't matter. If I choose the other dimension, all that would change is that all these values would be positive, and when I solve for m, I'd still get a negative 17. Because that's the sign convention that you have to use for bending moment. That's the sign convention you have to use for shear force. And that's the sign convention you have to use for axial force. I know it's a little jarring, but that's just the way it is. Okay, so let's see what happens now. I should probably finish this off. I think you can see that if you sum forces in the x direction and set those equal to 0, what do you get? You just have the axial force. So in this particular problem, there is no axial force. So now let's redo this and look just to the right. It's so small that our free body diagram, the geometry, is unchanged. But what does change is this 500-pound force. Now we're just to the right of it, so it's no longer on this free body. But the value at D and E are still there. And the applied moment out here at the end is still there. And our dimensions are unchanged. So you see the big difference? Just to the left, you include the force. Just to the right, it's not. Now, it's on the other body. If I look at the mate to the left, that 500-pound force is now over there. We didn't lose it. We did not consider it. It's just somewhere else. And again, I'm going to assume positive axial force, positive shear force, positive bending moment. And we're going to do the same process. Now, what do you think is going to happen to our bending moment at this point when we infinitesimally move from the left of the force to the right of the force? You expect any change? What's the moment arm of this force in the original case?
0.
So what's it going to be when it's not there? It's not even going to be considered. So it's probably not going to have any effect on our moment. So let's see. So again, I'll go back and I'll sum forces using right-hand rule at the cut. Now again, with right-hand rule, and I'm summing moments, not bending moments, just moments, what kind of moment is that? Positive or negative? Negative. And then these two 500-pound forces create what kind of moment about the cut? Positive or negative? Negative. So there's my 500 pounds, moment arm of 10 feet. The second one, 500 pounds, moment arm of 20 feet. And then the applied moment at the end, minus 2,000 pounds. It doesn't take much to look back and say that's the exact same equation. So our moment is unchanged. So the moment is not instantaneously affected when you go from the left under applied force to the right. Now as we move farther over, you would see some probably change, but not so the moment diagram doesn't jump up or down. What about the shear force? So if I sum forces in the y direction, let's see what I've got. So my shear force is acting up. And I got 1, 2 shear forces, messed up. Acting down, 500 pounds down, 500 pounds down. That's it, right? So my shear force is equal to 1 kip. So just to the left of that force, my shear was 1.5. Just to the right of the force, it instantaneously changes to 1. What's the difference between those two? What is the change in shear?
500.
It's 500 pounds. And why? Because the force is 500 pounds. So as you go under or pass by a concentrated force, your shear will change exactly the amount of that value. So if I were to make a plot of the shear force as a function of x, I'm plotting the shear force, and I'm worried about this point C, then it's coming in, I don't know what the value is, but it's coming in on the left side at 1.5 kips, and then it instantaneously drops down to 1 kip. And you can see that's the change in the shear right there. It's exactly equal to the force. So it's hard to say what the actual value of the shear is at C. It's multi-valued. So we always only care about the largest value, which would be just to the left. That's what you'd have to worry about.
So the bending moments will always be the same.
The bending moment at C will be the same. It won't jump up or down. The shape of the bending moment from the left side of C to the right side of C will be something different, but you won't have a jump. So we're going to keep this in our pocket, that the change in shear is going to be equal to the forces, and later we're going to use that in kind of a shortcut way to measure the variation of shear force and bending moment. All right, so we'll stop this one.